Hello, I am Ted Dangelmayer, and thank you for joining us today. I know most of you are familiar with our team, but just as a reminder, we're a consulting group that provides strictly professional services. So we don't sell products like ionizers, as an example, and have worked with many of you over the years and enjoyed some very interesting engagements, and have gathered a group of experts. And Arnie is one of our key experts, members of the team. He is one of the world's foremost experts on ionization. So I'm sure you will learn a lot from him today. And I would ask you to feel free to submit your questions in the chat box. And we can also unmute you if you'd prefer to ask them verbally. Glad to do it either way. And with that, I will turn it over to you, Arnie.
Okay, thank you, Ted. I'm assuming everybody can hear me okay. We're going to be talking about ionization selection criteria today. We're going to talk about class 0 applications for ionizers as well. The one thing we're not going to include today is electrostatic attraction. We have another webinar on clean rooms that we give periodically, and it's covered, in quite a lot of detail in that particular webinar. So let's go on to our, all right. Mouse not working. There we go. So our webinar tutorial today will cover some ionizer basics. We'll look at ionizer fundamentals, and we'll look at the nuclear and corona ionization technologies. We'll run through some ionizer selection criteria, how you choose an ionizer for a particular application. We'll talk about some practical considerations in the selections of ionizers. And we'll talk about ionization for class 0 and what the industry standard ESD control program document, S2020, we'll look at what that says about ionizers as well. So right on to ionizer basics. Primary ionizer functions are to basically neutralize charge. That's why we're using an ionizer. We're particularly looking at the insulators and isolated conductors because these are not, there's no way to remove charge from these items with grounding. If you could ground the isolated conductor, it wouldn't be isolated anymore. But if you ground an insulator, nothing really happens. Ionizers will also counteract tribal electrification. The ability to generate charge on materials in an ionized environment is lower than it would be if there was no ionization present. Remember that ionization is a CDM countermeasure. It's not for HBM. We don't use ionizers to neutralize the charge on people. It just wouldn't work. In any case, remember that it's almost always to solve a CDM related problem that we're using the ionization. And as I mentioned, it can reduce contamination in clean rooms. How do ionizers work? It's not very complex. We have an insulator. We never know ahead of time whether it will be positively charged or negatively charged. So what we want to do is charge the gas molecules in the air. We want to charge them both positively and negatively because we want both polarities present to neutralize the charge on objects whose polarity we don't know ahead of time. So if we have a positively charged object, it's going to attract the negative ions from the air. And if we have a negatively charged object, it's going to attract the positive ions from the air. And when it does, a charge exchange occurs at the surface. We have neutralized the charge. And when the charge is neutralized, it no longer attracts ions to the surface. So opposites attract, difficult as the physics is. So now let's take a look at our nuclear or alpha ionization and X-ray ionization. These are types of ionizers we use. In alpha ionization, the source is an alpha particle source. It's polonium-210. That's what we use. And what happens is that when the alpha particle is emitted by the polonium, it bangs into the nearby gas molecules. And by nearby, I mean that the alpha particle only travels about 2 to 4 centimeters in air before it gets stopped by its collisions with the gas molecules. Now, when it collides with the gas molecule, it will knock an electron out. So we have a gas molecule that has lost an electron. It's now a positive ion. We see here because it has 1 less electron than it had before. Now, whoops, sorry. Now, our dislodged electron over here can't exist in air for very long before it gets captured by a neutral gas molecule. So we have a gas molecule that now has an extra electron. It's negatively charged, and it's what we call a negative ion. Now, the interesting thing here is that you're always going to be producing a pair of ions. For each electron that's dislodged, we get a pair of ions so that the ionizer is always in balance. You always have the same number of positive and negative ions being produced. Now, if we had a soft X-ray generator that would generate a photon, that would pass by the gas molecules in air and essentially do the same thing that the alpha particle did. It will dislodge electrons from the neutral gas molecules, and as it does, it will produce these ion pairs. Now, electronic or corona discharge ionization uses electronics to produce ions. What we're using is high voltage on a sharp emitter point or a thin wire to create ions. What we're doing is using the sharp point or the very thin wire to increase the electric field at a particular location high enough so that we can indeed produce ions. Now, the high voltage that we apply can be different types. We start off with AC ionization, where we just produce high voltage by stepping up the line voltage, apply it to a grid, a bar, or a blower containing an array of emitter points, and this will produce your ionization. We should keep sensitive parts at least 30 centimeters away from the AC ionizer because there are high electric fields at the emitter points that may cause damage. Now, steady state DC uses DC of both polarities. It's fed to either grids, bars, or blowers, or a large array with discrete pairs of emitters. It's the most common type of ionizer in ESD-sensitive applications. We're always using this type of ionizer in blowers, in some ionizing bars, and it's because we can adjust the balance of the ionizer. It's the most common type we use in sensitive applications. Now, there's another type of DC ionizer called a pulsed AC or pulsed DC ionizer. And these systems generate both polarities by alternating the high voltage from positive to negative. And typically, the high voltage is applied to either a single or a closely spaced pair of emitter points. And it's most often used in rooms. These types of systems will move ions greater distances than the other types. We'll talk about that in a moment. So it's used in rooms where the ESD CDM sensitivity is greater than 100 volts. We don't use it in very sensitive situations. So here's some drawings of the types of ionizers. You see an array of emitter points. You see a high voltage transformer attached to the emitter points. And as the voltage changes from 0 to 7,000 volts to minus 7,000 volts in the sine wave, we produce ionization when the voltage exceeds a threshold. So when we get over about, maybe perhaps 3,000 volts, we start to produce ionization. We produce ionization as long as we're over 3,000 volts, but you can see that the ionization isn't produced 100% of the time. So the efficiency is very low with AC type ionizers, and we generally have to have a lot of airflow past the ionizer to assure that we get usable levels of ionization in our work areas. But this is a common type of ionizer. It's been used for many years. Here's a drawing of our steady state DC ionizer. You see discrete emitter points. You see a positive and a negative high voltage supply. If we keep the emitter points close together, we get a very good balance of ionization, but we lose a bunch of the ionization due to recombination. The positive and negative ions go to the opposite emitter points. And we, again, have to blow a fair amount of air past the steady DC ionizer to make sure we get good ionization in our work area. Because we are able to adjust the positive and negative power supplies, we get to have a very good balance possible, and we can use this in very sensitive applications. Keeping the emitter points close together gives us a good ion balance. Separating them far apart gives us more ionization, but can lead to hotspots where we have only positive or only negative ionization present. So we need to be careful about matching the spacing between the emitter points to the available airflow. And finally, here's our pulse DC ionization. Again, you have positive and negative power supplies, but we're alternating. First, we turn on the positive supply, make a cloud of positive ions. Then we turn on the negative supply, make a cloud of negative ions, and we adjust the timing and the levels of ion production so that we get balance down in the work area where we're trying to neutralize static charge. The efficiency, because you're not doing both polarities at the same time, is fairly high compared to the other types of ionization. So this is the type of ionization that would be used in a high ceiling room where we want to move ionization from the ceiling down into the work area. You can even use pulse DC ionizers with no airflow available. They are adjustable so that you can get ionization at usable levels even without airflow. So this is one of the methods we consider when we have a low airflow situation. So how do we select the ionization? How do we choose from the many, many different types of ionizers that are available in the work area? There are some selection criteria here. Do we use a corona ionizer? Do we use an alpha ionizer? There are capabilities of both types that are very interesting in the applications that we have in the electronics industry. I've highlighted in yellow some of the more important ones. Ionizer balance. Corona ionizers typically 10 to 20 volts, but with feedback control, you can get the balance down into the 1 volt range. Alpha, on the other hand, intrinsically 0 volts. There's nothing is needed to maintain the balance of an alpha ionizer. The only instruction you'll get from the manufacturer is to assure that the case of the ionizer is grounded, because that's important for its operation. But other than that, it's always going to be at 0 balance. When you install corona ionizers, you need to have power. You have to supply power to them. Typically, you have to keep them about 150 millimeters or 6 inches from your sensitive product, because corona ionizers do have an electric field. And by comparison, alpha ionizers, no power required, and you can mount them as close as 30 millimeters from the product. In operation, corona ionizers will have a varying maintenance interval. They will typically have monitoring and alarm to make sure that they're kept in balance, to make sure that you know if there's a failure. These are all operating options that you have. On the other hand, alpha ionizers, there's a 12-month maintenance schedule. You just have to check them at 12 months. And here's a very interesting thing about alpha ionizers. There is no failure mechanism. The only failure that they have is that if you use them too long before you check them and replace them if needed. But during that operating time, there's no possibility of failure, so you don't have to worry about them. Some cases, that's a very important criteria. Other things here, you'll be able to read. You'll get a copy of the webinar today. So what are ionization selection criteria? Well, fortunately, there's a document from the ESD Association that can help you with this. It's our technical report TR 3.0. It's called Selection and Acceptance of Air Ionizers. And what it talks about are the things that are important when you do select your ionizer, and how you get an ionizer and check it and decide whether to use it. So the first two issues that it talks about is, of course, number one, charge neutralization. How well does the ionizer neutralize static charge? And the second thing it covers, and this is very unique in terms of standards documents, is it tells you that if you're going to use an ionizer, you should test for the impact on the static problem. Very interesting. It says ionizers should do something. Also a very interesting approach to the matter. We basically say that if you're going to use an ionizer, you should be able to demonstrate that something in your ESD control regime has changed because of the ionization being present. We'll talk about that in a little more detail in a moment. Other considerations, there are environmental considerations, there are installation considerations, there are operating considerations. You know, of course, there's a cost consideration, but nobody really cares about that very much. And then we'll talk about all of these items as we go along here. So how do you know how well the ionizer is working? Well, you have to do some performance testing. You need to test the ionizer to see how well it neutralizes static charge. So again, fortunately, we have documents at the ESD Association that will help you do this. The document we're talking about now is STM 3.1. Its last issue was 2015, and there probably will be another issue very soon of that document. It is the only ionization standard worldwide. Everyone worldwide uses this document for testing ionizers. Now, the other thing that's talked about in TR 3.0 is the effects of ionization. It says, if you're going to use an ionizer, there should be an effect that you can measure. So if you're concerned about ESD damage, there should be less ESD damage if the ionizer is present. If you have a problem with the production line hanging up, there should be better production line uptime and line speed if the ionizer is there. If contamination was your issue, you should see less particles. If your airborne particle count was an issue, again, you should see less particles. But in every case, there should be a reason that you're using ionization, and you should be able to test that you have achieved what you were looking for when the ionizer is present. So, well, the instrument that's specified in the document is called the charge plate monitor. And what you see here is a blow-up diagram of the elements of the charge plate monitor. So we start off with this isolated conductive plate here. And I've made it transparent, obviously, so you can see what's below it. It's isolated on a set of standoffs. Underneath the plate is some type of probe that will measure the voltage on the plate. It's typically a non-contacting probe, but there are charge plate monitors that use a contacting method to measure the voltage on the plate. So we have this isolated plate. It's isolated from a nearby grounded surface, and it has an effective capacitance of 20 picofarads. Now, connected to this plate is a power supply so that we can charge it to a known voltage. We have this voltmeter, non-contacting voltmeter or field meter, or it could be a contacting voltmeter. It's attached to the plate, and it's basically monitoring the voltage that we see on the plate. And then we have a timer here that starts when the voltage drops below 1,000 volts and shuts off when the voltage gets to 100 volts. That's our measurement. So these are the elements of the charge plate monitor. Charge plate monitors come in many different types. You see here 2 full-size charge plate monitors. We have the 6-inch isolated plate, and then we have these portable charge monitors that make essentially the same measurement, but are portable. You can walk around in a factory with them very easily and do spot checking on your ionizers. And what you have is a field meter that has an isolated plate unit attached. And this other item here is our charger that charges the plate to a known voltage. So either handheld or full size, we can use charge plate monitors to determine the operation of the ionizers. So what do? What are our performance tests? They're specified in STM 3.1. The first test is a decay time or discharge time test. In this case, we charge the isolated plate to 1,000 volts. We measure the length of time necessary to reduce the plate to 100 volts. And then we repeat the testing with the opposite polarity, charging to minus 1,000 volts and measuring the time to reach minus 100 volts. So what we've defined as our discharge time is the time necessary to reduce the charge on the isolated plate from 1,000 to 100 volts. Now, we're also concerned about the balance of the ionizer, because if an ionizer is out of balance, it can actually charge objects that are nearby it. So we don't want that to happen. So to measure the ionizer balance or offset voltage, we ground the isolated plate momentarily to remove any residual charge. And then we place the isolated plate in the ionized area and note any change that occurs in the plate voltage. Is the ionizer going to induce a charge on the isolated plate? Now, for pulsed ionizers, it's normal for the voltage to swing between positive and negative values, so that when we're testing pulsed ionizers, we're going to write down the peak positive voltage and the peak negative voltage and call that the offset voltage. Here's a little picture of a handheld ionizer being used to check a handheld CPM or charge plate monitor being used to check the small ionizer on the left here. This little box here is an analyzer that will start and stop at the 1,000 and 100 volt levels and give you the time that it takes to discharge. So what we do here, first of all, ground the plate, verify 0 volts DC, charge it to over 1,000 volts. Place the charge plate approximately 12 inches or 12 inches away from the ionizer, or where you actually do your work, where the product is processed. That's actually where you really want to know how well the ionizer is working. So choose a place to place the meter, the charge plate monitor, when you're going to make this measurement. The charge plate, when you charge it over 1,000 volts, as it decays below 1,000 volts, the timer will start. The timer will stop when it reaches 100 volts, and you verify that the time to reach the targeted voltage meets the manufacturer's specification or your own in-house specification. And then repeat the same measurement, charging the plate to minus 1,000 volts. So charge to 1,000 volts, place it in front of the ionizer, and watch the discharge from 1,000 to 100 volts. Now, if we're going to do our offset balance measurements, once again, we ground the plate, verify it's at 0. We place it 12 inches downstream from the ionizer or where the product is processed, and then wait the manufacturer's specified time. Typically, this is 1 to 5 minutes. 1 minute with all of the ionizers that are nearby, and you might have to wait 5 minutes in a low airflow situation with a pulse DC ionizer on the ceiling of your room. Again, you're going to make this measurement, verify both the manufacturer's specification and your in-house requirements for offset voltage or balance. So we've talked about charge neutralization and the impact on the static problem. So what are the environmental considerations here? Well, certainly airflow. Airflow has a major impact on ionizer performance. And one of the things we need to be careful about is that the airflow must reach the charge surface. We'll talk about that again in a further slide. Clean rooms, we have to be sure that the ionizer materials and operation must be compatible with the clean room. We don't want to introduce contaminants in the clean room by bringing in ionizers. Humidity and temperature. These have a minor impact on the ionizer operation unless there are large swings. If there are large swings of humidity, you may have to choose ionizers that have their balance monitoring built in to avoid a swing in the ionizer operation. But in most work areas, there isn't a wide swing in humidity and temperature during the workday. Usually it's fairly well controlled. Some installation considerations. You have to be concerned about the distance from the charred surface. You'd obviously like to put the ionizer as close as possible, but there may be considerations of movement, of something operating in the area that you have to be concerned about. So distance is an installation consideration. The closer you're out to the charred surface you can get, the faster the ionizer will work. Power distribution. You have to be concerned about how you bring power to the individual ionizers. There are ionization systems that will distribute power using high voltage cabling. There are ionization systems that use low voltage cabling. There may be reliability issues that you need to be concerned about there. Your ionizer may need some type of feedback control to maintain its operating conditions, depending upon the sensitivity of the products you're trying to protect, depending upon the variations in the environment, humidity, temperature, and airflow that may occur. There are operation considerations and cost you don't really concerned about, but we'll talk about these in more detail. So some of the operating conditions, certainly safety is a consideration. Is the ionizer safe? Remember, you are putting high voltage there, so you need to be concerned about how you are being protected from that high voltage. If you had a clean room, you might be concerned about particle emissions. Ionizers do make some EMI and ozone. They do require maintenance, and let me say this right out front. There are hardly any no maintenance things in your work area. Ionization is not going to be the first. So don't let anybody sell you a, quote, maintenance-free, unquote, ionizer. We need to be concerned about the reliability of the ionizer, and that may be reflected in the warranty that's available. And cost is not a big deal. So let's look at some of the safety requirements. First of all, electrical. High voltage ionizers with exposed emitter points should have the points or wires current limited. This is an absolute requirement for safety. There's a really easy way to tell if an ionizer is safe. When the salesman brings the ionizer to you for you to evaluate, ask them to touch the emitter points when the power is on. If they start to sweat a lot and fidget and try to avoid the issue, you may have learned something about the safety of the emitter points. But many ionizers have been designed so that you can just walk up to that high voltage emitter point, put your finger on it, and you'll feel nothing. It is possible to design for that. Ozone is a byproduct of corona ionizers. It's a small quantity. You should, in general, think about keeping ozone-sensitive equipment away from the ionizers, or, basically get an evaluation unit and see if it produces ozone in an amount that's hazardous to something else that's ozone-sensitive in your environment. Radioactive safety, the manufacturer of the alpha ionizer must be licensed by the NRC. And the manufacturer and the user must comply with the government regulations. They aren't very difficult, but you need to do them. Installation, you must always have an installation that conforms with mechanical and electrical safety codes. I'll give you an example that I worked with a company that installed room ionization. And in most cases, we were able to use a self-adhesive type Velcro, very strong, that would hold the ionizers to the ceiling. However, in California, they said, our code says you must attach that to the ceiling with a positive attachment. So when we installed ionization in California, we always had to screw it to the ceiling or use metal clamps to attach it to the ceiling. different places will have different mechanical, electrical, and safety codes, and you must comply with whatever is in the local area. This is especially true of international installations where the electrical and safety codes may be very different than they are in the United States. We always recommend that ionizers should have evidence of a third-party safety inspection. UL, TUV, there are many, many different safety organizations that will inspect a product and give you a certificate that that product is safe. One thing I would mention, you've all heard about CE marks, I'm sure. These are the marks of inspection marks that are used in Europe for products that are acceptable there. The thing to remember about CE marks is CE mark is a self-certification. You don't have to go to a third party to put a CE mark on your product. I've always thought that that's very nice to have that CE mark, but if it could pass CE, the requirements are the same for the safety organizations. So why not turn it over to a third party to do the safety inspection for you? Always look for those safety inspection stickers. Shock hazards from ionizers. Oh yes, they are related to the high emitter output current or the use of high voltage cable and connectors. A previous ionization standard had a 100 microamp current limit at each emitter point. We were told for legal reasons we had to take that out of the standard. Believe me, 100 microamps is actually really too high. 100 microamps at 10 kilovolts is a memorable experience. We always, point to a 25 microamp current limit as at each emitter point, not at a central controller, but rather at each emitter point as a good safety level. In hazardous locations, lower limits may be advisable. In fact, some of the hazardous applications of ionizers are in explosive environments or flammable environments, and there are definitely lower limits advisable and specialized ionizers that are designed and certified for use in those types of areas. So what are the ionization problems? Well, EMI and ozone first. They're produced by corona ionizers. Always test an ionizer sample to ensure there's no interaction with the production process. Particle emissions, they're related to the emitter point materials and the ion current level. There are choices of emitter point materials that will reduce the particle emissions to the lowest possible level. These are single crystal silicon emitter points that produce the lowest particle levels, and they're especially applicable in silicon semiconductor applications, which, as you may imagine, are very extensive worldwide. We can also use tungsten, titanium, and other materials for less critical applications where particles are not as much of a concern. Particle collection, different than particle emission. Particle collection is the collection of particles on the ionizer itself, particularly on the emitter points. And it's related to what is in the environment. The chemicals that are in the environment will very often greatly affect the rate at which particles collect on an emitter point. So we want to reduce the airborne molecular contaminants with filtration to reduce our maintenance requirements. In the early days of using ionizers in clean room, where the chemical filtration wasn't very good, we sometimes had to clean ionizer emitter points weekly. When we got into better clean rooms with better filtration, and when the filtration of these airborne molecular contaminants became even more necessary to protect the product, we found that the maintenance interval went from 1 to 2 weeks to 6 to 12 months. So removing those chemical contaminants was good to protect the product and was good to protect the ionizers. So what are some of our other operating considerations? Well, first of all, maintenance. All ionizers need maintenance, period. I don't want to, get into any, distinctions here. That all ionizers will require maintenance. The maintenance interval is determined by checking the ionizer periodically and determining when it needs to be maintained so that it doesn't go out of balance. There are no maintenance-free ionizers. The best I can say that the maintenance interval on an alpha ionizer is the longest, and that's typically 12 months. But within that 12-month period, every other type of ionizer will need multiple maintenance operations. Reliability. Do ionizers need to be reliable? Well, you are typically working 24/7, 365, and the ionizer needs to be working 24/7, 365 because it's there to protect your product from static problems. So you want the ionizer to be reliable. Warranty, often an indication of the reliability. What we always say is don't buy an ionizer with a 90-day warranty. Ionizer manufacturers should have confidence in their product and extend a warranty that's at least 1 and perhaps 2 years long, that there should be no problems that you see from the ionizer over a long period of time. Cost, this keeps coming up. I guess we should get it out of the way once and for all. First consideration in cost is obviously the equipment cost. How much does it cost to buy the equipment? Equipment cost for ionizers is definitely more than what it would cost you for a wrist strap. So the equipment cost is going to be an issue. The installation cost, what do you need to do to install the ionizers? Ionizers typically use a very low amount of power so that you can use many ionizers in an installation, except in the case where you have ionizers that might have heaters in them. This will increase the power consumption dramatically. And when you're installing ionizers with heaters, you need to be concerned about providing power to them all. An ionizer that uses 2 to 10 watts of power, you never really are concerned about. But when an ionizer starts using 300 watts or more of power, then you need to be concerned about how many ionizers you're installing and do you have the power capabilities to power them. Operating cost, very low. For ionizers, you know, the power consumption when they're operating is very low. And unless, again, you have heaters, and then in which case it will go up. Maintenance costs, you do have to do maintenance. Someone has to go out there and clean the emitter points periodically, check the balance of the ionizer. That's a cost that you need to be concerned. So you have 4 different costs here that you need to add up to determine whether the presence of an ionizer is cost effective. Cost effective, interesting. We talk about the cost of discovery. And in general, the cost of discovery, in other words, what it's going to cost you to find out you have a static problem that can be solved by ionizers, is typically going to be between 10 and 100 times the cost of the ionizer. Why? Well, here's the problem. The problem is you had a static problem. And how did you know you had a static problem? Typically because you have production losses. And the production losses are higher than you find acceptable. So that's how you know you had a problem, production losses. Now, you have to go through a period of analysis. You have to find the cause, and you have to find trial solutions that mitigate that cause. And while you're doing that, do you stop producing? Usually not. So you continue during this time of finding the cause and trial solutions. During that time, you continue to have product losses. You've decided to implement a solution. You know what the cause of the problem is. You're going to order ionizers to solve the problem. Of course, you'd like to call the ionizer manufacturer and say, send me 100 ionizers immediately. And the ionizer manufacturer is going to say, we have a lead time. It's going to be 2 to 4 weeks before you get your ionizers. So 2 to 4 weeks before you get your ionizers, another week or so to install them. And during that whole time, you're continuing to have process losses. So that's the cost of discovery. All of those product losses in the time it takes to identify the problem, find the cause, implement a solution, that cost is usually 10 to 100 times the ionizer cost. So what is the lesson here? Ionization should be installed when a facility is built so that you do not ever have the static problem that causes those production losses. Think about that. Okay, now we're going to move on to some practical considerations for ionizers. What do we need to be concerned about? Well, as I mentioned before, we need to be concerned that the ions must reach the charged surface. So here you see an insulator. It's charged on both sides, as insulators will be, and it's sitting on that work surface. We bring in the ionizer. The ionizer has airflow. It brings the air down to the charged object on the work surface and neutralizes the charge on the surface. However, it can't get to the charge on the side of the insulator that's lying on the work surface. And remember, I said you can't discharge the insulator by contact with ground, so it doesn't matter what that work surface is made of, that charge is not going to go away from the insulator. So what do we need to do? Well, what we need to do is lift it off the work surface so the air can get to both sides, and then the charge will go away. So once again, everywhere you're using an ionizer to neutralize charge on your product, you must make sure that the ionization can get to the surfaces of the product where it's charged. The airflow must reach the charged object. How fast do ionizers work? Well, here's a table of discharge times from 1,000 to 100 volts. You see the first item there, normal air with 60% RH. Humidity will eventually take the charge off of a charged object. It will neutralize a charged object. But as you can see from the number there, it takes greater than 10 hours to do that. That's a long time. Now, with ionization in its various forms, you see that the time to neutralize the charge from 1,000 to 100 volts is anywhere from 1/10 of a second to 500 seconds. Depending upon the type of airflow you have. Ionization must have time to work. You have to make sure that the application allows enough exposure time to the ionized air. In other words, if your object that you're trying to neutralize is whizzing by on a conveyor, you don't have very long to neutralize the charge on that object, and that's going to affect what type of ionization you use. But what you can see from this table is that no matter what type of ionizer you use, the neutralization time is much faster than if you just had humidity to neutralize the charge on a product. Why is faster important? You ask, why is faster important? Because problems caused by static charge are always two-step events. First, you create the charge, and at some later time, it creates a problem. So if you can use an ionizer, you can basically narrow the window in which those two events have to occur. So if it takes 36,000 seconds to get rid of the charge, that's a very big window. But if I can get rid of the charge in 10 to 20 seconds on a workbench, that means that if the charging of the object and then the contact of something with ground has to occur in that 10-second window, or the problem doesn't exist. We have solved the problem. So the faster we can get the ionizer to work, the narrower the window for those two events to occur, and the less likely it will be that you will have an ESD problem. When we're using ionizers, we want to optimize the location, get it as close as possible to the place where the charge is causing a problem. Mark the ionizer position. I can't emphasize this more. The problem, years ago, people asked me what was the one thing we could do with an ionizer to make it work better. And what I said was drill 2 holes in the base and bolt it in place so that it can't move. Nobody generally wants to do that, but it's really a good idea to mark on the workbench where the ionizer goes so that anybody can do just a spot check and verify that the ionizer is where it's supposed to be. We also want to mark the tilt angle. If the ionizer can be tilted, we want to make sure that it's always pointed where it's supposed to be pointed, which is obviously at the work surface, where the work is being done. Can you believe this? This is an unretouched photo, believe me. This is obviously an ionizer that has not had the maintenance it's supposed to have. It's interesting, the reason we found this ionizer, because it was tucked away behind some other equipment, was that we had an ESD event detector, and the ESD event detector kept going beep, 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 because of the arcing that was going on inside this sad ionizer. So basically, you've got to have a maintenance program. Maintenance program is easy. Install the ionizer, check it after a month. If it's in balance and working, do nothing, go away. Come back in another month, check it again. Working, in balance, okay. Come back in the 3rd month, slightly out of balance. Clean the emitter points, retest it. If it's now working, you know that your maintenance interval is 2 months.
Arnie, I just wanted to add a thought here.
Okay,
That
please,
event detection, when we did the event detection, we were, I don't know, 75 feet away, and we picked up the signal.
Mm-hmm.
We were way on the other side of the room.
Right. You shouldn't have to use an ESD event detector to determine that an ionizer needs maintenance. So basically, go through the process, determine the maintenance interval, and make sure that, you know, whatever you have to do in your company to get it to be part of the general maintenance program, that you actually do that. Maintain ionizers in the calibration system. They do need to be checked and the calibration verified at least annually, if not more. Here's an example of sealing ionization for 300 millimeter. This is a photo area, as evidenced by the yellow lights. Photo areas are very important for ionizers because the reticles, these are the negatives used to produce the semiconductor products. These reticles are one of the few items out there that are actually sensitive to electric field, that you can produce an ESD event on a reticle just from the change of an electric field. No contact needs to occur. So we need to make sure that all the surfaces in the photo area are neutralized, that there's no charge, so that if someone is carrying a photomask through this area, they aren't subjecting it to changing electric fields, which could cause ESD damage to the reticle. So what you see here is a large array of sealing type ionizers on the ceiling to make sure that everywhere in this photo area, the charge has been neutralized. Many, many different types of ionizers. They're available for ISO class 1 through class 8, which is a very wide range of clean rooms and clean areas. They're used for semiconductor front or back end process. They're used in electronics assembly. They're used inside production equipment. They're used in inspection stations. And there are bars, air assist bars, blowers. There are lots of different types of ionizers here. You see on the bottom here, this is an alpha ionizing bar. These are some alpha spot ionizers. This is an airflow ionizing bar. It has an input for air to increase the range of the ionization. You have overhead blowers, you have benchtop blowers in many, many different types. Lots of different types of ionizers. When we look at blow-off and compressed gas ionization options, there are cartridges, there are blow-off guns and nozzles. There are many, many different types of ionizers to use in blow-off applications where you not only want to neutralize charge, but perhaps you might want to remove particles from the surface as well. Ionization, because it neutralizes the charge, makes particles easier to remove. All right, we're getting close to the end here. There are some class zero considerations. The first class zero consideration is, can you solve your problem with static dissipative materials? We always favor using passive solutions first to solve the problem. So if you can avoid the problem by using a static dissipative material, let the charged part contact the dissipative material and safely dissipate the charge. Easiest way to do it, most reliable, no personnel input is required. It's always going to work for you. If you can't use static dissipative materials to resolve the problem, then you continue with the possibility of using ionization. You want to confirm the effectiveness with and without ionization. What was the problem? Are you getting ESD events that you can measure? Do they go away when the ionizer is operating? Is there charge on an object you're concerned about? If the ionizer is present, can you measure with a field meter and determine that the charge has gone away? Conventional ionizer offset voltages are typically plus or minus 25 volts, but for class zero, they may not be low enough. There are Corona ionizers available that will get you under 1 volt in ionizer balance. And there are obviously nuclear or alpha ionizers that will give you 0 volts. So there are options when you have very, very sensitive product of different ionizers to select. You typically want to select your offset voltages between 1/2 and 1/10 of the most sensitive device. So for instance, if you had a 50 volt device in your operation, you might want to have ionizers that maintain a plus or minus 5 volt offset voltage. Whether it's 1/2 or 1/10 depends on your feelings of how much margin of safety you want. But there are ionizers available that will give you what you're looking for. And of course, we must have process compatible decay times. There's no point in having a decay time of 60 seconds if the product is only exposed to the ionizer for 3 seconds. So the ionizer decay time must be fast enough for the existing process flow. Some examples, trim and form, test handlers. These are 2 areas where we have metal-to-metal contact. It's unavoidable. You have to use metal dies to trim the parts. The test handlers have metal contacts in their sockets. The metal-to-metal contact is not avoidable. You may have insulated pickups, you may have insulated surfaces, you may have extremely sensitive device. There may be multiple testing stations where you have to go from one testing station to the next. And there may be ungrounded test and transfer locations. Ionizers eliminate the charge when the metal-to-metal contact cannot be eliminated. So for instance, in a test handler, if your product is charged, when you put it into the socket, you're going to have voltages induced on the pins of the device. And when they touch the metal pins of the socket, you have ESD. The socket itself is an insulator. It has to be to separate the contact pins. The package of the part is an insulator. We have contact and separation of different insulators. Is charge going to be generated on the socket? Most likely it will. So now you have charge on the socket. You have an uncharged product comes in, but the charge on the socket induces a voltage on the pins, and you get ESD when they get inserted into the socket. So the ionizers are there, first of all, to make sure that there's no charge on the product, but second of all, to make sure that if any charge is generated on the sockets, it gets neutralized before the next part comes in. Now, test operations, fairly quick. You may have to have an ionizer that will neutralize charge in a few seconds in this type of application. In contract manufacturing, we've got circuit board assembly, we have surface mount, we have assembly of components onto an insulated circuit board that contains other insulators. So we have both a CDM, charge device model, and CBE, charge board event risk. So we basically have a lot of insulators that are being put together, and we need to be concerned about the charge on those insulators. We use ionizers to neutralize the charge on the circuit boards before placing components on them. We can do that. We have time before the circuit board comes into the pick and place machine to neutralize the charge. We use ionizers to neutralize charge in any operation where metal-to-metal contact may occur. So we want to make sure that we have no charge on objects if they have unavoidable metal-to-metal contact. We talked about test handlers. Anytime you attach a connector to a circuit board, you have the possibility of ESD because you have metal-to-metal contact in the connector. So we use ionizers to neutralize the charge on the boards, on the connectors themselves, to make sure that we're not getting ESD when we have unavoidable metal-to-metal contact. We use ionizers to neutralize charge on the component supply reels in the automated equipment. Suppliers of ESD-sensitive components are almost always really good at packaging their products in good ESD-safe materials. However, there are other components that are not considered to be ESD-sensitive, resistors, capacitors, lots of other things. And very often the reels that they come on are insulators. So you have a very large charged object in that supply area of your pick and place machine. So we sometimes use ionizers to make sure there's no charge on any of the component reels in the feed area of the automated equipment. Remember, most pick and place operations occur too rapidly for ionizers to help. Ionizing inside the pick and place machine rarely has any effect that you can measure. You need to find another way to protect the class 0 components. Oh, a bunch of pictures of contract manufacturing issues. Burn-in, big issue. Whenever you're loading burn-in boards, you need to make sure that there are ionizers present because there's always metal-to-metal contact occurring. When you do circuit parts insertion, we tend to want to get the charge off of the circuit boards before they go into the pick and place operation. When you're doing circuit board loading, manual, you have soldering operations. You want to make sure that there is no charge present because that soldering iron is grounded and it's going to cause an ESD event if it touches a charged object. Many applications where you have metal-to-metal contact, you need to be sure that you're not involving a charged object in that metal-to-metal contact. Class 0 feedback control. If you're going to do sensitive, handle sensitive devices, you're going to want to assure that your ionizer stays in balance. And what you see here is a block diagram of an overhead ionizer over a work surface. And on the work surface, they've placed these 3 sensors. And they go through this feedback control network and they control the ionizer balance in these 3 fans. So you have a separate sensor under each fan to maintain the balance on the work surface. And these types of ionizers with this on work surface sensor are able to get better than 1 volt accuracy and stability. If you're not getting 1 volt when you do this, check your test instrument to make sure that it is stable at this level. Here's another picture of just a single work surface ionizer. Now we only have 1 sensor for it. And once again, we have this feedback control circuit to maintain the balance and to tell you if the ionizer goes out of balance and needs maintenance. Last item is S2020, the worldwide static control document. There's a version of S2020 in the European union, and it's used internationally, but essentially it's got most of the same things that S2020 has. Now, back in 2014 was the last change of S2020, and there were some major changes in how they dealt with ionization. The first thing is they lowered the offset voltage requirement from 50 volts to 35 volts. They were trying to conform to the JEDEC recommendation that ionizers and isolated conductors should be less than 35 volts. Okay, so where that changed. Now the other change they made is there used to be a separate specification for room systems, because room systems work differently. When you measure them on the work surface, there's a different situation that you're dealing with. They took out that different specification, which means that all ionization now has to meet that 35 volt requirement. But a room system ionizer that's adjusted for 35 volts is not going to work very well. So what do? Well, you could put a tailoring statement in your S2020 ESD control program that would say something along the lines is that the room ionization will be used in conjunction with local ionization to assure that the 35 volt limit is not exceeded. That can be done. The other thing you can do is just don't include it in your ESD control program. You don't mention it, you don't have any requirements of the system. You're still going to make sure that your ionization in sensitive areas is less than 35 volts, but you will be able to use that room system for other issues like contamination control. So finally, in conclusion, air ionization is an important part of a static control program. It's there to neutralize the charge on the insulators and isolated conductors. It's not there for people. It's not there to replace any other part of the static control program. Ionization, applying it successfully, requires an understanding of its capabilities and its limitation. What it can do, what it can't do. Is it working fast enough? Is it close enough? These are all things you'll need to determine. Selecting an ionizer for a specific application requires an understanding of device sensitivities. You need to make sure that you choose an ionizer with a balance level that's appropriate for your sensitive devices. And you have to understand the manufacturing process. You have to make sure that it works fast enough with your product flow. And you have to make sure that it meets your static control program requirements. Is the discharge time compatible? Does it do what you want? Is it balanced at the level that's appropriate for the sensitivity of your devices? These are things you need to know in order to choose that ionizer. There are ionizers optimized for class 0 applications down to the 1 volt level. We use ionizers in disk drive manufacturing where they have to be at 1 volt or less. This is possible, but the type of ionizer needs to be correctly selected and it needs to be properly applied. And what I usually finish all of my presentations with is the statement at the bottom: static control is no longer optional. It is the price of admission to working in the electronics industry. If you're not doing static control in your electronics manufacturing operation, you're not getting the yields that your process is capable of. So that's all I have to say right now. And Ted, if you can run us through some of the questions.
Well, thank you, Arnie. Well done as usual. And what I'll do at this point is to, let's see what happened here. I see. What I'm going to do is unmute everybody and invite questions. Love to hear your thoughts. Let me see if I can do this correctly.
Okay, we'll leave these.
Yeah, so you individuals can unmute yourselves now and ask your questions.
Hello, can you hear me?
Yes, thank you.
Good morning, it's California time, and good afternoon in New York time. Anyway, I have a couple of questions, please. My name is Tai Tron. I'm working in for 26 company. The first question I have is if we do have the feedback controls in place, which means that I cannot, I stop checking the ionizers monthly. Is it possible?
Well, feedback control will certainly extend the maintenance interval. But as I mentioned earlier, you need to determine what that maintenance interval is. And you do that by, when you first install the ionization, checking it once a month to make sure it's in balance. If it's in balance, you do nothing. You keep checking until you find that 1 month, either the discharge time is too long, the balance is slightly off, and you need to clean the ionizer, and you know that however many months it took you to get to that point, your maintenance interval is 1 month less. Now, having feedback controls in your ionizer will definitely make that maintenance interval longer. As I mentioned, in the semiconductor industry, typically now the maintenance interval is 6 months or longer for actually doing ionizer maintenance. So basically, you will, with an ionizer that has feedback control, you will have less maintenance to do, but you do need to find out how long that maintenance interval needs to be for your application.
Okay. What is the qualified vendors who can do maintenance on these ionizers?
Qualified vendors. Well, that's an interesting term. In general, people go back to the original manufacturer of the ionizer to find out if they have maintenance people or can recommend maintenance people. But I don't know of anything, that any organization that qualifies anyone to do ionizer maintenance.
Okay.
The interesting thing is years ago, we did, a little Pareto chart of maintenance issues. And no surprise to us, the largest bar on the Pareto chart was no maintenance at all.
Yeah.
So that's still a problem. Doing maintenance is really simple. It usually involves, a swab dipped in IPA, and, you just swab the points with it. It's not very difficult. But basically, we see a lot of ionizers that aren't getting the maintenance they need.
Now the charge plate monitor, the voltage is generating can be able to damage high sensitive components or parts at all.
The charge plate monitor, certainly you've got a charger for the charge plate monitor that will charge that plate to 1,000 volts. And you could take that charger and destroy everything in your work area, probably.
Okay. Gotcha.
So basically, in general, when we're doing ionizer, measurements, we make sure that there's no product on the work surface at that particular time. But, as long as you're careful and don't touch the product, you're not going to damage it with the ionizer measurement.
Okay. With the heaters on, will that impact performance of the ionizers?
Usually not.
Okay.
It shouldn't. Turning the heater on shouldn't change the ionizer performance. The manufacturer should have taken care of that in some way. We do know that when the air is warmer, it's more active, and the ionizers actually work a little bit better. They work a little faster when you heat them up. Okay. But other than that, there shouldn't be any significant change in the operation of the ionizer when the heater's on.
And there's a related question on that topic, and it was, why would you use an ionizer with heat?
The reason is that sometimes in areas that get cold cold in the wintertime, they may, heat the air. Usually they're trying to save money and not heat the air as hot as they should. And sometimes the ionizer blowing at someone makes them feel a little bit cold. So that's generally the reason we see ionizers, with heaters. I can say without, exception, there's a north-south differential here that that ionizers with heaters wind up in areas that are in the north part of the country, and we never see them in places in the southern part of the country. I've seen many ionizers with heaters in Minnesota. I have seen no ionizers with heaters in Arizona.
Mm-hmm. Among all the ionizers, which one you recommend?
There are many good companies out there. We tend to recommend ionization for a particular application, and then let the user discuss it with the various manufacturers. We will, our recommendations are basically for companies that we know produce, good ionizers, ionizers that will last a long time, ionizers will do what they say they will do. But there are, a number of companies out there that you can choose from.
Mm.
Other questions?
We had a request to unshare Arnie's screen so that we can see people, but I think the video is shut off for everybody. Maybe we can make it an option.
You'd at least see all the boxes and you'd see kind of who all's there.
Yeah.
And some people have.
I can certainly unshare it, and then you guys can do what you need to do.
Yeah. Let's see, where did the chat go? So, any other questions?
Hi, Ted. Hi, Ted and Arnie. I also hear Ginger in the background. This is Manny from Qualcomm. How are you guys doing?
Hey, Manny, how are you?
I'm doing good. Doing well. Thank you. Excellent. A very informative presentation, Arnie.
Thank you.
You mentioned you covered alpha and the other type of ionizer. How about photon ionizers?
Yeah, photon ionizers have been around for a while. They're getting a significant amount of use in the flat panel display industry. The photon ionizer or X-ray ionizer is unique in that it produces ions all along the travel path of the photon, so that it can ionize a very large interior of a machine without any airflow being present. So we find, in applications where you have a large substrate, like in flat panel, where the glass panels can be greater than 3 meters square, the photon ionizer is a very useful ionizer to use in those applications.
You've covered handlers, and we deal with that a lot at my company. But now the challenge is that our handlers are now going at a faster operating speed. And we're talking about less than 3 or 2 second dwell time. That's transition between the device and test and all that as it inserts into the test socket. What would you recommend be an ideal type ionizer that can cover that type of a process?
When you get down into that time frame, you're almost always going to use a compressed gas ionizer of some sort. So it could be an air-powered ionizing bar. It could be an ionizing nozzle. These are the types of ionizers you'd experiment with to see if they met your requirements.
I forgot to mention the second part, the important part as well, that the test socket areas designed around the handlers now are restrictive. I'm talking about very tight spaces. And so for the most part, I don't think a bar ionizer, even fan ionizer would be suitable for that high speed.
There may be an application for an alpha type ionizer, which you can bring very close to the socket.
I see.
And we'll keep that socket neutralized.
Oh, okay.
I've seen that work very effectively.
Alpha ionizers, huh? Okay. Okay. You also on your presentation you covered the 6-inch plate and the 3-inch plate. As you know, there's also the 1-inch plate. Is when you, of course, and it's been in my experience when I perform verification using a 1-inch plate, it's not the same performance and results from as compared to a 6-inch or a 3-inch. At what point do you use a 1-inch plate?
When the 3-inch plate won't fit. I mean, basically you're using a small plate because the large plate won't go in where you're trying to make the measurement. The 1-inch plate typically has much different characteristics because of its low capacitance. You know, what you're going to do is make some measurements and decide what's acceptable with that particular plate.
Okay.
Generally, we find that the smaller plates will have longer discharge times. So maybe you need to allow a longer discharge time with your small plate. But again, you know, with ionizers, there's no industry requirement that says you must do this other than keep the balance under 35 volts. The actual balance you have, the actual discharge time you have is your company specification using whatever measurement method you want to use.
Okay, thank you.
While we're waiting for others to think about their questions, we have a question about where this webinar could be downloaded. We will post it on our website within the next few days. So you'll be able to access it there.
So can most ionizers can be able to handle higher voltage greater than 15K volts?
It is possible to design an ionizer with higher voltages, but not really.
In reality,
it's not a good idea. Okay, 2 reasons. First of all, you are using a method called corona ionization. It is a phenomenon where you get a low current discharge, and that ionizes the air. As you raise the voltage on the emitter points, you will eventually get to a what is called the spark regime, where the ionizer will just start making sparks from the emitter points. And these can create electromagnetic interference. These are not a positive thing. They will erode the emitter points quickly. There's no reason to raise the voltages higher than 15 kV. If you go to higher voltages, you have higher currents, you have more particle production, the ionizer will be more difficult to balance. And the reality is there's no reason to do that. Most ionizers have been designed to efficiently produce ionization, and they don't require going up to very high voltages to do that. So there are a number of negatives involved with you know, raising the voltage to very high levels.
What exactly soft X-rays?
Oh, okay. If you're using X-ray ionization, the manufacturer will give you information about how to protect it. But when you're using X-ray ionization, the energy level is fairly low, and typically almost any sheet of metal will stop the X-rays. It usually requires about a 1/4 inch or you know, 60 millimeters of a plastic insulating material to stop the X-rays. The other things that you need to do for X-ray ionization, you need to make sure that when you construct the cabinet that the X-ray ionizer is inside of, that it uses lap joints rather than butt joints to make sure there's no X-ray leakage at the joints. And at least in the US and probably elsewhere, you're required to have a shutoff, that if the cabinet that contains the X-ray ionizer is opened, that it automatically shuts off the ionizer.
What is the ideal decay times versus volts when we're dealing with high sensitive components?
Well, decay time, again, is there's no absolute specification for decay time. So if you ask me what's the best decay time, the answer is always as fast as possible.
Right.
You want to get the charge off your object that could be damaged by ESD as quickly as you can. I would say that the great majority of facilities I've been at that are contract manufacturing, where you're assembling components, the discharge time requirement is typically 10 seconds, between 10 and 20 seconds. Now, if you're in a machine that's operating rapidly, obviously you have to have an ionizer that operates quicker than that. But just in general, I would say for electronics assembly, 10 to 20 seconds. And for room system type applications, between 30 seconds and 2 minutes.
Okay.
Hey, Arnie?
Yes.
There's a question in the chat from Robert. He evidently took your maintenance emphasis to heart. And so he wants to know the best way to clean the emitter points. And should the annual test be done before the cleaning or after?
Good question.
Probably both.
Good question. Okay. So as far as how to clean, typically ionizers that have emitter points, you take a swab, you dip it in IPA, isopropyl alcohol, and you just push it over the points, rotate it a couple of times. The whole process of cleaning an emitter point should take 10 seconds or less. If you have lots of emitter points, then there's lots of 10 seconds, but basically the cleaning process is generally very, very simple. When I talked about that maintenance procedure, I was saying operate the ionizer, check it. Remember that I didn't say clean it first. Always check it first. And if it's not out of balance, don't do anything. Don't clean it. You don't have to clean it if it's still in balance. When it goes out of balance, that's when you need to clean the emitter points and assure yourself that after you've cleaned them, the ionizer is back in balance.
And that's a way to figure out the right interval.
Right, that's how you figure out the interval.
And Robert, you might standardize if you have somebody going through and you've determined that every 6 months is adequate, then still test without cleaning to make sure that things are working the way you expected. And then I often would test after cleaning to make sure you didn't break something. You know, the emitter points can be kind of delicate. But basically, you're just knocking a little dust bunny off the end of the tip.
Yeah, your ionizer should never get to the level you saw in that picture.
And some ionizers have a little brush that you just go back and forth and it just sort of knocks them off.
Ah, yes, that's a good point. There are ionizers available with either manual cleaning that Ginger described, and there are some that have automatic cleaning. Typically, it means that at the beginning of a shift, you turn the ionizer off, you wait till it stops, you turn the ionizer back on, and now the emitter points have been cleaned. So there's both automatic and manual cleaning of some ionizers.
Arnie, is that like a self-cleaning oven? I mean, how does it work?
Centrifugal force, actually. There's a hub in the middle of the ionizer, and as the ionizer slows down, the brushes that are inside there come out. They swipe the emitter points until the ionizer stops. Then you turn it back on. And when it comes up to speed, the brushes retract into the center hub again.
So you're talking about the fan that's inside the ionizer.
Yeah, these are all fan ionizers that have the auto cleaning.
Wow, you learn something every day. I'm done now.
All right.
That's good. That's good to know. Is there any risk of during that cleaning process, contamination in some cases?
Yeah, I mean, generally what the manufacturer's instructions say is that you should wait about 10 minutes after the cleaning process before you start working. So it's something you do, you come up to your workstation, you turn the ionizer off, you turn it back on, and then you do all the other things you need to do to start working. And by the time you've done them, you know, any particles that are coming off are gone.
Okay.
Just to mention, every place I've worked, you never turn the ionizers off. This is certain kinds of ionizers that have built-in cleaning but I found in manufacturing where I worked, if they got turned off, they often didn't get back on again. So
yeah, right. Mm-hmm.
We just left them on all the time. In fact, sometimes we'd remove that on-off switch.
Right. Yep. That was the second improvement for the ionizer. Beyond bolting it, it was get rid of the on-off switch so they can't turn it off.
Arnie, it's Jeremy Smallwood here. Greetings from the UK. I was just wondering if when you're using a charge plate monitor to evaluate how an ionizer is working in a particular situation, do you tend to choose one with a plate size which is as close as possible to the target that you're neutralizing, or do you not worry too much about that?
You know, it depends on whether you're in a specialized situation or not. In general, it doesn't matter. You know, the relationship between the charge plate monitor and the part is not that important. What we are concerned about is, you know, whether the measurement method is giving us information that, you know, first of all, conforms to standards. And we'd like to have it be representative so that we have some idea of what is happening on the part. So if that's important, if it's important to know what's happening on the part, then you might want to choose a smaller plate to give you that information. But in general, we're just looking for the ionizer performance. Does the ionizer do what we expect it to do? Again, if you have a special situation, you're doing research on a situation, it may be very useful to use a smaller plate size then.
So Arnie, there's another question from Andrew that says, when performing ionizer checks or readings, is it okay to perform these readings off the manufacturing floor or off the ESD floor away from manufacturing? And actually, we're trying to test the function of the ionizer in the location where it's being used. So whenever it gets moved, you no longer know what you're testing. So we would recommend testing it at the work spot where the most work is being done. If it's a clean room situation, you're worried about contamination and the ionizer fails and you could move it easily somewhere else to adjust it, that would probably be okay. But generally speaking, we recommend checking them at the work location.
To emphasize,
on an ongoing basis, you always want to check at your work location because that's where you're concerned about the ionizer performance. Now, when you're selecting ionizers and you want to compare, you know, 2, 3, 4 different ionizers and their performance, that's the kind of checking you might want to do offsite in a controlled environment so that you know that all of the ionizers are in the same position, in the same, you know, same working conditions. But once you have ionizers in your, you know, static control program and they're working in your facility, then you usually want to check them in the actual work location.
There's another question here about 3 units with 3 fans. Should each ionizing unit be isolated in some way, or can they be test them individually, or is that not necessary?
Well, I mean, again, this is one of those things where it depends on the manufacturer. There are some give you an example. If it's an AC ionizing blower, it's an overhead blower, it has 3 fans, they're all going to be connected to the same power supply. They're all going to be pretty much the same. There are no separate adjustments for each of the fans. Now, when you get to DC ionizers, there may be adjustments for each fan separately. So it varies between the manufacturers and the application, whether you have that facility to adjust the fan separately or not.
But Arnie, if you tested it at the work location, isn't that what you really want to know?
Oh yeah, always.
I mean, qualifying, you might want to qualify them separately to make sure they were all even. But at the work location, you want to test where your product's going to be.
Always. That's the proof of the pudding, is how it's working in the actual work location.
Yeah, and you'll find that you can test, you know, if you're testing with the 3 units, you can test them individually, you know, a foot away and get a sense of what each one is doing. And then in the aggregate at the work location where you're working on product needs to be, you know, well ionized.
there's a question for Nick Pimpinella at the headquarters office. Somebody wants to know how they can read the ANSI ESD standards on the internet.
I don't know, Nick, did you want to answer that?
So any standards that are available complimentary, you can find on our website by visiting the store. Otherwise, you would have to purchase a copy of those standards.
Okay, so basically the answer is some of our standards are free and downloadable. Others you do have to pay for. Less than the cost of an ionizer. Any other questions?
I don't see any here.
Sounds quiet.
Yeah. It's your last chance.
In any case, thank you all for attending. It's been a pleasure. And I will see you at the next Dangelmayer webinar, no doubt.
And also, we have an announcement coming out for a TR53 certification course that will be coming out later this week. So if you're interested, keep your eyes peeled.
Mm-hmm.
And it's remote, so you can do it from your home location. And I see we have Joshua Yu on the line from Korea. Thank you for being up in the middle of the night.
Yeah, right. Middle of the night for you, Joshua.
Yeah, and very late for Jeremy.
Uh-huh.
Just about to go and get a beer.
Mm-hmm.
Get enough for all of us.
Yep. Okay.
All right.
Thank you, everyone.
Thank you all. Have a great rest of the day, week.
Thank you. Thank you so much.
Thank you. Bye-bye.
Yep.
Bye.
Good day.
Thank you, Arnie.